now move to the next bullet point that concerned the notion of prime elements. So our standing assumption is that R is an integral domain. And I want to define the notion of divisibility. So an element A in R divides B if there exists C in R such that B is equal to AC. And you can see that this is the same as saying that B belongs to the principal ideal generated by A. Contains B, or in other words, the ideal generated by A contains the ideal generated by B. In this case, we denote, so notation, A divides B by the vertical line. The next definition, I say that A in R is irreducible if when we write A as a product B times C, then either B is a unit or C is a unit, but not both. So when A is not a unit itself. So a non-unit element is irreducible if we cannot reduce it into two non-unit elements. And we say that an element P inside R is prime if, again, P is not a unit, and if P divides the product of A and B, it implies that either P divides A or P divides B. When we look at the ideal definition of divisibility, we can note that P is a prime element, P is prime, if and only if the principal ideal generated by P is prime. Is a prime ideal. Note that these notions depend on the ring. For example, 2 inside Z is prime and irreducible. but 2 inside Q is a unit. For the ring of integers, we took it for granted that irreducibility, this definition, is equivalent to being prime, using this definition. And in general, being prime implies being irreducible. So if P inside R is a prime element, then P is irreducible. The proof goes as follows. So let us take a prime element P and suppose that P is equal to some product A times P, like in this definition, and we want to prove that either A or B is a unit. But by the definition of a prime element, either P divides A or P divides B, so I can choose one of those. Without loss of generality, P divides A. So A can be written as R times P. And therefore we write our original equation as P is equal to AB, and we plug in A equal to RP. So P R B. And by moving PRB to the left side, to the leftmost side, we get that P times 1 minus RB is equal to 0. But P is a non-zero element, and we have an integral domain, so 1 minus RB must equal 0. So 1 is equal to RB, which says that P is a unit. And so we prove that a prime element satisfies the definition of an irreducible element. However, not only we cannot prove that an irreducible element is prime, but we can also construct a counterexample using a very easy subring of the complex numbers. We are going to construct an example of an irreducible element which is not prime. For our integral domain, take the ring Z adjoin square root of minus 5. We can write it as Z adjoin alpha, where alpha squared is equal to minus 5. And it is a subring of the complex numbers. Because I don't want to write square root of minus 5 all the time, I will write the elements of R as pairs A I will write the elements of R as pairs x plus y alpha, where x and y are integers. This element has, this ring has the norm function defined as x plus y alpha minus norm of x plus y alpha is the square of the complex norm. So it is x squared plus 5y squared. Note that n of x plus y alpha is always a non-negative integer because x and y are integers and 5 is an integer as well. Moreover, n is multiplicative. So n of a times b is equal to n of a times n of b, because the norm on the complex numbers is multiplicative. Therefore, if A divides B, then the norm of A divides the norm of B as integers. Moreover, if U is a unit element, then by multiplicativity we have that 1 is equal to the norm of 1, which is the norm of U inverse, and this is equal by multiplicativity to the norm of U times the norm of U inverse. But norm is a non-negative integer, and because these two numbers multiply to 1, it is non-zero. So n of U must equal 1. So U is a unit. If and only if its norm is equal to 1. Now consider number 6. It is the product of 2 and 3 on the one hand, and on the other hand it is product of 1 plus alpha times 1 minus alpha, because it is 1 minus alpha squared, and since alpha squared is minus 5, we get that 1 minus minus 5 is equal to 6. So now take number 2. 2 divides 6, and 6 is equal to 1 plus alpha, 1 minus alpha. But 2 does not divide either of the factors, 1 plus alpha or 1 minus alpha. And this is because the norm of 2 is equal to 4, and it does not divide the norm of 1 plus or minus alpha, which is equal to 1 plus 5 is equal to 6. So 2 divides 6, but not either of the factors. So 2 is not a prime element. I left here important facts about the norm, and I freed up some space for proving that 2 is irreducible nonetheless. For this, let's follow the proof. Let's say that 2 is equal to A times B. Then the norm of 2, which is 4, is equal to the product of norms of A and B. And since the norms are non-negative integers, we can only have two cases. So case 1 is when we have 2 times 2, or 1 times 4. But let us look at the norm of the element A. So let's say that it is n of A1 plus A2 alpha. So the norm is equal to A1 squared plus 5 A2 squared. And we see that this quantity for integers A1 and A2 can never be equal to 2, because we either get 1 from when we let A1 equal to 1, and if we let A2 be equal at least 1, then we already get 5 in here. So the norm 2 never appears. Therefore, 2 times 2 does not happen. And so either the norm of A or the norm of B is equal to 1. So possibly by changing notation A and B, we assume that the norm of A is equal to 1. And recall that we observed that an element U is a unit if and only if the norm of U is equal to 1. So it means that A is a unit. So we proved that in this decomposition, A equal to BC, one of the factors was a unit. And we got an element 2, which is irreducible, but not prime. So in general, we should be really careful about distinguishing irreducible elements from prime elements. We have just seen an example when an irreducible element was not prime. And a very reasonable question to ask would be when it actually is, under which conditions irreducibility is equivalent to being prime. And in the rest of the lecture, I will work toward explaining one of these conditions. So if we assume that every element in our ring R admits a factorization into irreducibles, then it turns out that irreducibility and primeness are equivalent exactly when this factorization is unique. So the definition of what I have just said. R, our domain, is a unique factorization domain commonly called UFD if factoring terminates which means that if we have an element A in R, a non-zero element, if it is not irreducible, then we factor it into a product of A1 times B1, and if where both of them are not units, are non-zero and not units, and if one of them, at least one of them, for example B1 is still not irreducible, we factor it further, so we get A is equal to A1 times A2 times B2. And if one of these factors is still not irreducible, we continue factoring into, let's say, A1, A2, A3, B3, etc. And the condition here says that at some point this process will stop. So at some point we will arrive to a product of irreducible factors. And the second condition says that this factoring is unique. And this means that if we have two factorizations, P1 through Pn and Q1 through Qm, two factorizations of an element A, which is not a unit and not an R, not a zero. Then these two factorizations should be essentially the same. In particular, they have the same number of factors. And possibly after renumbering, Pi differs from Qi only by a unit. Pi is equal to Qi times a unit. Or it's the same as saying that the ideals that they generate are equal. So let us express this first condition in terms of ideals. Proposition. Let R be a domain, then the following are equivalent. First, factoring terminates, and second, every increasing chain of principal ideals let's say A1 is contained in A2, is contained in A3, etc. If every increasing chain of principal ideals stabilizes. So it means that there exists a big enough n such that for every I and j greater than n, the ideal generated by I is the same as the ideal generated by j. So after n, all the ideals here stay the same. So at some point we only get equalities. Let us see how this works. Proof. For the forward direction, 1 implies 2. We will show contrapositive. That is, assume we found an infinite chain of ideals. A1 is strictly contained in the ideal generated by A2, which is strictly contained in the ideal generated by A3, etc. ad infinitum. That A1 belongs to the ideal generated to A2 means that A1 is factored as C1 times A2, and see that C1 is not a unit, because otherwise the two ideals would coincide. Now A2 belongs to the ideal generated by A3, so we can factor A2 into C2 and A3. And now C1 and C2 are both non-units. And also note that A3 is not a unit, because since we want to increase the ideals, A3 does not coincide with the unit ideal. And so we continue this factoring. So we get C1, C2 through Cn, A, n plus 1, and we can still continue. And in this case, factoring does not terminate, which is a contradiction. And so we wouldn't be able to find an infinite chain of principal ideals in a domain where factoring terminates. Conversely, let us take an element A which is neither a unit nor 0, and let us try to factor it. Let us factor it into A1, B1. So if this is a proper factorization, so if A was not irreducible, then it would mean that if A1, B1 are not units, then it would mean that the ideal generated by A is properly contained in the ideal generated by A1 and the ideal generated by B1. Okay, let us assume that A1 is not irreducible. Then we get a proper factorization. Of A1 into A2, B2. And then we would get that A is strictly contained in the ideal generated by A1, which is strictly contained in the ideal generated by A2, and strictly contained in the ideal generated by B2. And if we continue factoring the first factor, always, then by finiteness of chains, we would get that eventually this would stabilize at some point, so we get that AI is equal to AI plus 1. And so we would factor the first factor until we get an irreducible element, and then we can move to the second factor. And thus we show that the ascending chain condition, this increasing chain condition for principal ideals, ensures that factoring terminates. And now onto the result that I announced several minutes ago, that if R is a domain where factorization terminates, then the following are equivalent. First, the factoring is unique. And just to remind you the definition, it means that R is a unique factorization domain. And the second condition is that irreducibility is equivalent to primeness. So every irreducible element is prime. Let's see the forward direction. So we assume that R is a unique factorization domain. And we prove the contrapositive. So let P be irreducible, but not prime. And since it is not prime, then by the definition of being prime, there exists a pair of elements A and B such that P divides the product of AB, but does not divide either of the elements. Does not divide A, and B does not divide B. Since P divides AB, it means that there exists an element C such that AB is equal to PC. And then we can factor A and B into irreducibles as well as C. And so we get a factorization of AB into irreducibles and a factorization of PC into irreducibles. And we see that P does not appear as an irreducible element in the factorization on the left because P does not divide either A or B. So we get two factorizations for one element, which is the product of AB, which is also the product of P and C. So we saw that if there is an irreducible element that is not prime, this would imply that a certain element would have non-unique factorization. And now let's prove the opposite. So 2 implies 1. to check that the factoring is unique, we assume that we have an element A which admits two factorings into irreducibles, or equivalently into prime elements by assumption. P1, Pn is equal to the product of Q1 through Qm. And now let us prove it by induction on, for example, M. It will be a descending induction, so we will get rid of the factor Pn and then work our way down to P1. So we know that Pn is an irreducible factor, which also means that it is prime. And by definition, a prime element, if it divides the product, it necessarily divides one of the factors. Pm divides Qi. By possibly renumbering Qi's, we can assume that I is equal to M, without loss of generality. It means that Qm is equal to U times Pn, but Qm is also an irreducible factor in a factorization, and since it is irreducible and Pn is not a unit, it means that U must be a unit. And so we get that A is represented in the form P1 through Pn, or also Q1 through Qm minus 1 times U times Pn. And since the ring is a domain, it means that it satisfies cancellation property, so we can cancel out Pn on the two sides and get another equality of two factorizations, P1 through Pn minus 1 is equal to Q1 through Qm minus 2 times U Qm minus 1. And note that here this product is still an irreducible element, because we are changing an irreducible element by a unit. And so we get equality of two smaller factorizations, and we work our way down all the way to P1. So in a similar way we prove that Pn minus 1 is equal to U1 times Qm minus 2, and we factor it, Qm minus 1. In a similar fashion we factor it out, and in the end we are left with something like P1, P1 is equal to Q1 through Qk. But again, by irreducibility of P1, it is necessary that K is equal to 1. So an irreducible element cannot be decomposed further. And thus we conclude that ideals generated by pi's are equal to the ideals generated by the corresponding qi's, and n is equal to m. Examples of unique factorization domains are the integers, which you know really well, and some of you have already used it on your homework. Every field is a unique factorization domain because the condition of factoring is vacuous, because every non-zero element is a unit. And we will see next time that principal ideal domains, where every ideal is principal, are unique factorization domains, as well as if F is a field, then the ring of polynomials is a unique factorization domain. And a non-example would be z adjoint square root of -5. Because we saw that the element 6 admits two factorizations 2 times 3 is equal to 1 minus square root of -5 times 1 plus square root of -5. We saw that the element 2 is irreducible but not prime because it does not divide either this factor or this factor. But in fact, using again the arguments with complex norm, you can show that all of these 4 elements, 2, 3, and these 2 factors are irreducible. And so we found an element 6 which admits 2 non-equivalent factorizations.